present you some of the results on a novel back-end-of-line design for calibration of measurements on a high-frequency device, which is a SIGI APT up to 500 gigahertz. So first will be a general introduction of sub-terahertz waves and OnWafer sub-terahertz waves application and OnWafer TR calibration. And then I will expose you the motivation of a one-tier or in-situ calibration. And finally, results on both passive and active devices will be exposed up to 500 gigahertz. So advancement in electronics allows us to go higher and higher in frequency. And this opens up to novel applications such as short-range wireless communication or sensors for automotive or imagery for medical and security purposes. These waves are non-ionizing and non-harmful for the human body, and they can pass through tissues and clothes. In order to do so, RF designers have to rely on an accurate compact model and of the device. And of course, the parameters of this compact model have to be extracted through on-wafer device measurements. At high frequency, that means above 110 gigahertz, all this extraction proves to be quite challenging. So before talking about these challenges, here is a view of the measurement benches that we have at our research lab in Bordeaux. So we have multiple VNAs for covering frequency from 20 to 500 gigahertz with dedicated extenders, frequency extenders, and probes. In this work, I will present all measured data with picoprobe probes from 20 to 500 gigahertz. So of course, when we are measuring a device, what we see in the measurement, in the raw measurement, is not only the device itself, but also the entire setup contribution. And we want to remove this. And what we classically do to remove all the parasitic contribution of cables, connectors, and extenders and probes is a classic two-tier calibration. So first step is applying an algorithm, like in our case is a TRL on-wafer. And the second step is the on-wafer de-embedding. So the purpose of the first step is to push the reference plane, which is it's a mathematical representation of what we see, push it from the VNA down to the probe level. And the second step, which is the on-wafer de-embedding, allows us to push down to the DUT level, so that what we actually see is the device itself. The problem is that with the embedding, we rely on a description. These dummies that we use for the embedding are described as an equivalent circuit with lump elements. And these elements do not prove to be ideal by going higher in frequency. The other problem is that every time we measure these dummies and we want them to apply the embedding on the measurements, we are actually, we expose us to errors and uncertainty due to the fact that we are actually measuring multiple devices. So what we thought is that instead of having a classic layout of the back end of line that starts at the higher metal level, which in our case is metal 8, there are access lines that go down to the metal 1 level, which is the lower metal level, that is connected to the device. What we do is go down from the pads directly at an intermediate level, which is M3 in our case, where the access lines are located. And here, we go down finally to the device. So we are moving the reference plane from being at the edge of the access line at metal 8, we are moving in both vertical and horizontal direction at metal 3. So here is a upper view of a slice of the wafer. And we can see that we have improved our design also in order to reduce the coupling with the neighboring structures, which we have seen it's a problem at high frequency. And so to sum up, all we have it's the TRL standards, so the through, the pad open, which is our reflect that provide an open circuit at pad level, and the line, 110 and 500 gigahertz lines to provide TRL from 20 to 500 gigahertz. And also there is a pad load, a load structure for impedance correction. Then we have the devices under test that are shown in this presentation, which are the complete open and complete short, an open and a short at a lower metal level, metal 1, and of course the HBT. Both of these structures have been designed in a classic and an M3 back-end of line version, and they are compared. So first, here are shown the characteristic impedance and the ohmic losses. So as we can see, the classic line before correction is almost at 50 ohm, so it's quite good matched, but the M3 line is not, so we have to apply the impedance correction. This is the reason why we have to do it. And at the right, we can see the real part of the propagation constant, the ohmic losses, and as it's logic, we see that the losses on the M3 lines are higher since the dimensions of the line are smaller. So if we go on with the analysis on the passive structures, the procedure is as follows. So we take the raw data, the uncalibrated data, and we pass them through, for example, the pad open, of the complete open, and we pass them through a TRL calibration with impedance correction, and we got the corrected data for the complete open. We do the same thing with the complete open with the M3 back-end of line. So we pass them through the M3 version of the through, the reflect, and the line, with the M3 version also of the pad load for impedance correction. And we got the corrected data. The same thing is done for the complete short, and these measurements are compared to the intrinsic electromagnetic simulation made on HFSS. So where the ports are located where the reference planes are supposed to be. So here are the results on the passive structures. So capacitances for complete open are shown and inductances are shown for the complete short. C11 for port 1, C22 at port 2, and coupling capacitance between port 1 and port 2. And also, same thing is for the inductances, L1 for port 1, L2, port 2, and mutual inductance L3. If we focus on the complete open capacitances, we can see that measurement and simulation are quite, they match. Just in the 140 to 1020 gigahertz, we have some divergences. These are due to the measurement setup, since we have also experimented them on the simulation with probes. And the reason could be either a probe to substrate coupling, but since we have worked on improving the layout, this is the most unlikely reason of the two. Probably the reason behind this is the probe-to-probe coupling that happens with those probes, picoprobe probes, in this frequency range. Also, what we see is that for the M3 back-end of line, complete open, we have reduced the capacitances. They are from 0 to 3 femtofarad. This is because, as I said, we have moved the reference plane in both vertical and horizontal direction closer to the device. So now moving on to the active device. The procedure is as follows. We take the non-calibrated data and we pass them through the TRL calibration plus impedance correction, and we apply the embedding. So it's the classic procedure. We apply complete short embedding and complete open embedding, and we and we take this as a reference. So the reference plane, as you can see, is close to the device. Then the other step is to take our M3 version of the HPT, so the same transistor with another version of the backend of line. We apply the TRL calibration in the M3 version, and we got, without applying the embedding, we got the corrected data. Please note that the reference plane in this case is positioned in a different place, and this is the price to pay for not having the embedding. And then the third case is a mixed case, where we have the non-calibrated data that pass through the M3 TRL and complete short and complete open in the M3 backend of line version. And we have the corrected data for the HPT. And the reference plane in this case is at the same position as the first case. So here are the results on some figures of merit of the HPT. So current gain H21, Mason's gain U, and transit frequency and maximum oscillation frequency that are calculated from the two figures of merit above. If we analyze more in detail FT, Fmax, we can see that FT is constant and then rises with frequency, which is something that we also observed in simulation, and it's due to a second-order effect on the HPT. What is unexpected is the roll-off of Fmax in the lowest frequency range, up to 110 gigahertz. This is due to multiple reasons. Is due to the measurement setup, the probes that we have used, but also to we have experimented that in high-cum simulation plus electromagnetic simulation, and we can state that it's due also to a secondary effect on the transistor, inside the transistor. What is interesting to compare is the curves, these curves. We expect that since we have the reference plane at the same position, the orange and the blue curve should stick one with another. The thing is that for Fmax, we can clearly see that there is an offset in the orange curve, and also that the orange curve is more noisy. So this fact is due to multiple reasons. One of them, for sure, is the area of contact pads. Since we have measured these devices multiple times, and we have damaged the pads by placing the probes on them. So this could explain the noise that we see in the orange curve. Also, process variation could be another reason behind it, since we are measuring, of course, the same transistor, but we are measuring two different transistors with two backend of lines, so they are not physically the same. And as we can see, the collector current that is flowing inside is not the same. And also, the different access line resistance could explain this fact. But if we see if we compare the blue and purple curve, so the M3 TRL plus and without the embedding, we can see that we can conclude that there is an offset in all these figures of merit in FT and Fmax. But if you see here, the purple curve seems to be less noisy, seems to have a more flat behavior. This is because we are not adding up some additional matrix computation on the measurements of the device. So we are actually confident about this method, even though if we want to have a really precise measurement on the device, at this stage we cannot get rid completely of the embedding step. So thank you. the thickness of the dimensions of M3 have been reworked in order to try to have the 50 ohm impedance. But what we actually have seen is that we were not able to do it from the beginning, so we had to correct it. The thickness. The thickness, I cannot remember how much it is, but how much have been, but it has been like taken as to be able to have something coherent at the end, but I cannot remember the exact value of it. Yeah. We actually, we are testing also this way. We are also trying right now to go a bit further and then go down, and also trying to do the same thing at metal 8. The thing is that we didn't want to incur into like coupling between the two access lines if they are so close, since these structures are not so far. Port 1 and port 2 are not so far. So we are trying to we are already doing it, and we are going to test it if it's working. Yeah, that's.
And when we had a via stop actually sitting under the pad, where was the via stop for your transistor?
It's in.
Also sitting under the pad?
It's the same structure, going down, sitting down on the pads, and then goes down, and then the transistor just lays down at the.
So it's the same interface.
Yeah.
Maybe just a comment. You showed a parts of T as a figure of merit. So complicated to understand what is going on with your transistor.
Mm-hmm.
Is a suggestion you can just look at the normal unbiased parameters of transistor like junction capacitance, which people understand more. Because for you, the transistor does work, you don't care. You just need to prove that your calibration delivers trustable results, and then the rest you can just move on the process development engineers to let them do it for you.
Yeah. Okay.
Let's thank our speaker one more time.
Thank you.